All right, how's it going, everybody? We are here at the beginning of week three. We had a little delay yesterday because of some issues I was having with my setup here, but hopefully that's all going to be resolved. And we can kind of proceed on here with our topics here in chapter two. So, my plan today is for us to kind of get started on the chapter two things. One of the things today is that I'm going to as I've got kind of at the top of my document right here. Um, in the content in this week's videos, it's kind of like talk about what we're going to see here before we actually get into it. This week, we're going to cover the rest of chapter 2. Last week, we had 2.1 and 2.2. This week, we're going to get 2.3 through 2.7. These sections really are one nice collective group of topics here. They really do go together pretty nicely here, to the point where I'm going to kind of spread it around a little bit between today's video and tomorrow's video, as far as the topics that are in there. So in general, what we're looking at in these sections here is the ideas of computing and interpreting basic statistics that are associated with data sets. We've got the word statistics here in bold. I want to kind of briefly mention what we mean here. In general, when we think about statistics that we're computing, you see below, I've got some of the computations we've got in this section here. We've got our mean, median, mode. We're going to compute some quartiles and percentiles. We're going to discuss the skewness or the distribution shape of the data. Our interquartile range will be a good measure of spread. We're going to look at outliers and some ways that we compute those. We're going to try to not overstate some things about outliers, though. Standard deviation is probably our most difficult by hand computation. We'll do one of those by hand and one of them with technology today. And z-scores is the very last thing that's talked about at the very end of 2.7. That's going to be a hugely important topic for later in this semester, so we're just going to lightly introduce it now, but that's something that'll come up Z-scores will be a topic of discussion in probably about 10 or 12 sections later this semester here. So those are really important, but it's for right now that we're just doing kind of the simple parts with Z-scores. So before I kind of walk away from that list of things right there, I kind of want to say, when we talk about a statistic, I want you to remember that a statistic is a really generic word. What we mean when we say that a value is a statistic is that really a statistic is just any value that's been computed in association with a data set. So I just want to kind of point out that like not every statistic is useful. One statistic of a data set, perhaps I have a data set of 40 values. Well, one thing I could compute is what is the eighth value divided by the second value minus the fifth value. That would be a statistic for the data set, and I could give it a name. However, I'm assuming that you are, by the ridiculousness of what I just said, aware that like there's a very, very little chance that that statistic is going to actually mean anything to us, have any interpretable qualities that's helping us really represent the idea of the data in that set. So just be aware that like a statistic is technically like any value that you have computed using data, but not all statistics are useful. Dividing your eighth value by your second value and subtracting the sixth, what's that telling us? It's almost certainly nothing in all cases right there, right? So not every statistic is useful. Not every statistic that is useful sometimes is useful all the time. So what we kind of want to do in this section is see what are the spread of basic statistics that are generally computed in association with data sets. And we want to see that sometimes some of these are not good descriptors of the data set. In other cases, they're excellent descriptors of the data set. So aside from just performing computations in this unit, one of our other kind of things associated with this is making decisions. Is that data actually representative, or excuse me, is that statistic actually representative of the data set, or is that maybe a little bit misleading? So in today's video, this week's videos, I'm going to spread it around as I'm saying right here. It's not like I'm just going to do 2, 3, and 2, 4 today and do the rest tomorrow. I'm going to kind of do more of like the basics today and some of the a little bit more difficult things in tomorrow's video. In the next video, we will do things like estimating a mean from a frequency table. We'll talk, I'm going to talk quartiles today, but not percentiles. Those just get a little bit more technical in their computation right there, and I would rather talk about kind of bigger picture things today than technicalities there. Computing and interpreting z-scores, as I already said, super important for topics that are coming up later. So we'll take a look at that tomorrow. Typical shapes of distributions of data. That's sort of something that I'm kind of trying to like start us thinking about kind of future topics right there. We're going to look at so many histograms this semester, and we kind of want to be able to classify them into a couple groupings of saying, kind of giving labels to those different shapes that we're going to see from those histograms. And finally, there is a really smart dude about, I don't know, 100 years ago or something like that, that was teaching statistics and was just getting annoyed at his students kept on just computing statistics for things and being like, here's the descriptors of the data set. And so this is great. This is like a teaching story where this guy, the statistician, got so fed up with people just like computing statistics and assuming that they were representative of the data set that he went out of his way to come up with a really smart organization of data to create some very intentionally misleading statistics associated with some data sets to emphasize to people that it's not okay to just compute a statistic and assume that that is representative of the data. So the other thing we'll look at in the next video is this very special example of misleading statistics here. And this is just this example is just going to be really, really nice. It does a great job visually of helping you see that just because you've computed some statistics does not mean that you actually know what the data looks like. So it's sort of our little like warning right there of saying, don't be overconfident. If you've computed a few statistics, that might help you understand the data. But we don't ever want to think that a few computed statistics are going to truly capture the information associated with raw data. And then it always matters that we look at our data, that we look at graphs of our data, stuff like that. So those are the topics I'm looking to hit tomorrow. So what we're going to do today, as I'm saying here, is we're going to do, I don't know, I shouldn't necessarily call this the basics. Plenty of these things are a little bit weird here as well today. But we're going to do today, we're going to look at two different data sets. Okay, three different data sets in two different scenarios. And we'll look at a few by hand computations, and we'll also look at some technology-based computations. We can do, there's lots of different ways that we can go about computing a lot of these things. I'm going to use Excel. In the past, I have used the TI calculator, but I kind of don't like that in our online setting. It's a bit tougher for me to share that with you and you to share that with me. I know that some people use Google Sheets. Other classes use R and RStudio to compute some of these values that I've done in the past. But again, I think that's a little bit difficult in our online setting. So there's lots of options for us. And it's important that we kind of explore some of our technological options here. Maybe the last thing I'll say, since I'm talking about technology right now, to kind of wrap that up, is all College of the Redwoods students are entitled to a free copy of the full Microsoft Office suite, meaning Word, Excel, PowerPoint, all that stuff, right? Typically, it costs money if you don't already have it. But CR has sort of, in a sense, collectively bought a package where as long as you have a CR email, then you can get a free download for that. So if you want these things and you don't currently have access to them, then you can poke around on the CR webpage. I guess I could have found that here for today. If you need help finding that on the CR webpage, then feel free to send me an email and I'll try and help you navigate that one right there. I know that sometimes finding things at the CR page can be a little bit tough. So again, if you don't have access to those things, if you do not currently have those things, you do have access to them because you have a CR email. And so we can help get you things like Word and Excel, stuff like that. So we're going to start with a small, simple data set to look at here, and we're going to do some basic by hand computations. The purpose of this is really going to be more to draw some comparisons rather than to actually look at interesting data. In the second scenario, we'll look at some slightly more interesting data with some slightly more interesting computations here. So let's take a look. So this starts out not super excitingly right here. I am going to hit backspace a few more times here. Start with about the simplest data set that I could ever really imagine discussing right here, and we're gonna compare it to another data set after we've computed some values here. So again, this is like, I can't really make it much easier than this. We've only got 5 data points. They're all whole numbers. They're consecutive whole numbers. They're all positive. Like this is about as good as it's ever going to get right here. So let's just kind of do our basic computations here. Again, the important thing in a second is that we're going to compare our results from this guy to the next one. And we're going to want to kind of interpret what we've seen about the statistics that we compute here. So first things first, let's go ahead and find some things here. We're looking to find a mean. First thing I want to say about this is remember that this is just another word for average. When we compute a mean or an average, I kind of want I'm going to lay out some terminology here and some notation, by the way. In a given data set, it's pretty common to think of each of these as random variables. These are things that we are assuming have been, like, in a sense, randomly selected from a population here, right? I'm thinking of this as a sample. And so in this case, I might kind of think of these values as like x1 being 1, x2 being 2, x3 being 3. And in this case, it's a super boring list where the subscript on the x actually ends up being this value because I picked such a basic setup right here. The reason that I'm doing this is because what I want to be able to say is that a generic data point in this data set I might refer to as x sub I. It is the ith data point in the data set. So if you were to say what's the sixth data point, I would say x sub 6 is blank. And in this case, we don't have an x sub 6 because there's only 5 data points right there. All right. The reason that I'm doing this is because I just want to show you a little bit of mathematical notation that's going to be associated with this here. Whenever we compute an average, I'm assuming that all of us know how to compute an average here. We're just going to add all the terms and divide by how many terms there were. In this case here, 1 and 2 is 3, 3 and 3 is 6, 6 and 4 is 10, 10 and 5 is 15. So it looks like I'm getting a 15 over 5. And that's going to leave me with an average value here of 3 for the mean or the average. You should notice that 3 in this data set does happen to not only be a value in our data set, but it is also the central value that is located in our data set right there. Sorry, I'm gagging on my oatmeal right now. Some other things. Earlier this semester, we talked about fractions. In week 1, I said to you in a lot of cases, we're not going to reduce fractions. This is one of these great cases where we are mostly always interested in computing the fraction that is reducing it down and getting the value 3. If this weren't a clean division right here, we would certainly be interested in getting a decimal. Our entire next chapter, chapter 3, is all about probability, and that chapter is going to be a big place where we're going to keep things in fractions so that we can help interpret them. We will compute some decimals there too, but in chapter 3 will be a big place where we'll be interested in seeing things remain in fraction form. For a lot of these statistics that we're computing here, we'll go ahead and actually evaluate these fractions here. So what I want to show here is just some slightly alternate notation for this. A mathematical notation to represent adding up a list of objects is to use what is referred to as sigma notation. So that sign sigma right there is to represent add up a bunch of things. What are the things that we want to add up? We want to add up all the x values in our data set, right? If I'm thinking of these as x1 through x5, I want to add up each individual one of them. So this x sub I is sort of like my generic representative of the data set. It's not any particular one of these. This is any one of them depending on which value of I you choose. So what I want to add up here is all of the objects that look like x sub I. All I need to do to kind of finish describing this sum is say, well, what values of I might we experience? Well, in this data set, in any average, the value of I is always going to start at 1, the first thing in your data set. So we say in our summation notation, I starts at 1, and we put it on the bottom because it's our starting location. On the top, we'll put our ending value for I. Our final value for I is always going to be the number of items in the sample, right? That's because we're taking an average of all of the values. So it should always be that this ends at n, the sample size. In this case, I'm just going to write it over here. In this case, we have that n is 5 for us. But in general, n is always our sample size. We're always averaging all of the values from the first to the nth value, add them all up. So this just says do the addition. That's the numerator of our fraction. I could then divide by the total number of observations seen, and this will give me my average. So this is sort of my mathier way to write what it means to be computing an average. This says add up all of the variables x sub I, our data points, where I starts at the first object, and we're going to go all the way up to the nth object. And because we have n objects, this just says get all of it. This is my way of saying add up all the terms from the first to the last, where each of them is an x sub I. Finally, divide by n. I'm trying to introduce this notation right now because we're going to see a slightly grosser version of a similar idea coming up here when we come to standard deviation. So we've computed our average here, our mean. So let's also look at our median here. When I compute a median, and what I'm going to kind of do for myself, let me help myself out a little bit real quick here. Oop, that's not what I wanted. Okay, I'll leave it alone. When we're looking for a median, our book distinguishes between mean and median as one being the median being a measure of location, whereas the mean, the average, is a measure of center. In general, these are both referred to as measures of center, but I like that they distinguish these in saying that the median is a measure of location because I don't care what these values are. I just want to know what value is in the middle. A typical thing that I do when I compute a median is, since I'm hunting for the middle, I'll just remove the outsides until I get to the middle. That's my easiest way of doing this rather than trying to count stuff. So I remove the outer two most, and then I remove the next outermost two, and therefore whatever's left over has to be my median. That's all I'm doing to help me see what my median is going to be here. Sorry, I'm skipping some notational things. I want to stick with these notational things right here. In general, when we compute an average of x values, putting a flat bar over x indicates that this is the average of all of the x's. I had 5 x values here, x1 through x5 were the values 1 through 5, and to find x bar is to find the average of all of them. So this is our general representation of average here. We just found the median to be 3 by eliminating outer numbers here. Also, real quick, it absolutely matters that this is an ordered set right here. If we were chopping off not ordered terms, then we wouldn't have landed at the one that was in the middle. So whenever we're computing an average, it never matters if they're in order because addition can happen in any order just fine. For the median, I always use this cross-off method, and it really matters that they are ordered from low to high when I do that. Otherwise, I'm not going to end up appropriately having found the median. So our other notational thing to say here is that when we are computing the median, that we denote this typically, this is kind of unfortunate, it gets a capital M. I don't like that because I want to reference the data values as X's right there, but that's what we get. And the median that we just found in this data set, it turns out was also 3, right? It looks like they were the same right there. So what else are we looking for here? We're also interested in the mode, and we're interested in the standard deviation. So the mode is always our most common value. Out of all the values that we saw, which one occurred the most frequently? Well, what we can see in this case here is with our data set being 1, 2, 3, 4, 5, there is no one value that occurred the most frequently. In this case, it would therefore be acceptable to either say no value occurred more often than any other value. Therefore, we could say there is no mode. Alternatively, it would be equally acceptable to say the most common thing that I saw out there was 1, and it was actually tied with 2 and with 3 and with 4 and with 5. And so in this case, we could say every single one of those values, 1, 2, 3, 4, and 5, are all the mode of the data set. But you should really ask yourself, does that tell you anything? I guess that sort of, I think that no mode and all the values of the mode are telling me the same thing, which is that there is only one representative of each data point that's happening out there. So here, I'm just going to say for our mode, in this example, there is no mode. All right, so since there is not a value that's more frequent than all the other ones, we could say here that there is no mode. And again, technically, I think it would be okay to say that all of them represent the mode. But again, as I kind of said at the beginning, like every time you compute a statistic, if you're really going to give the answer of like every number is the mode, then like what have you really identified? And that sort of says to me that if everything's special, nothing's special, right? So That's kind of my take on the mode right there. If you see that there's no mode, that usually means that it's not really anything of interest for you to spend any more time thinking about. And I will certainly say average and median, I think that those represent 95% of the importance of measures of center, and mode represents like 5%. There are some data sets in which mode is a really good descriptor of the data, but it's pretty uncommon. It's pretty much all semester. Average and median are going to be two things that we're going to be mostly interested in here. So I think by far our most exciting computation associated with this data set is going to be the standard deviation. So let's go ahead and compute a standard deviation here. The standard deviation computation is certainly the toughest of these computations. I hope you didn't find any of these too challenging here. Add stuff up and divide by how many there were for the average. Chop off the ends and find what's in the middle for the median. Mode, see if anything occurred more frequently than anything else. So when we go to look for our standard deviation here, um, sorry, one second. So when we go to look for our standard deviation here, what we are going to compute, oh, and by the way, we're going to relate this also to variance. It's a very, very closely related idea right here. What we want to know is how far are things away from the average, right? And here's what I could do. I could take each of our x values and I could find their distance from 0. So I'm going to make a kind of a column here. This is going to be kind of my standard deviation section. All of my x of i's. What I want to know is how far are they from the average. Each individual term, how far away is it from the average? Well, I can add these up. How far away is 1 from the average? Well, 1 minus 3, that's going to give me negative 2. 2 minus 3, that's going to give me negative 1. It's 1 to the left of the average. 3 minus 3, 3 is at the average, so it's 0 units away. And 4 minus 3, that's 1 unit above the average. And 5 minus 3 is 2 units above the average. So in a sense, what we're trying to get a sense of with this standard deviation is we want to know, on average, how far are each of our data points away from the center. Well, if I find the average distance from the center, notice what I'm going to get here. If I compute the average distance from the average, negative 2 and positive 2 is 0. Negative 1 and positive 1 is 0. And 0 is 0. And you add 3 zeros and divide by 5, and you get 0. Right? So the thing to notice here is that it is always going to be the case. This is by definition of average. It's always the case that the average distance away from the average is 0. So it turns out that just doing this little bit of subtraction isn't helpful for us, because every single data set will always have the fact that the average distance from the average is 0. So here's what we do to kind of help emphasize this a little bit differently here. The thing that I like to think to myself is that things that are outliers should represent to me a much more significant deviation from the average. And so what we're going to do is we're going to apply a bit more emphasis to things that are further away. The other thing that I'd like to do here is I don't like the fact that this negative 2, in a sense, cancels with this positive 2 here, to suggest that positive 1 and positive 5, both collectively, then it would seem like they essentially have 0 deviation from the average on average. And that's a terrible descriptor here. The other thing that I think is more helpful for me is to think about the fact that 1 is the same distance from 3 as 5 is, even though 1 minus 3 gives negative 2 and 5 minus 3 gives positive 2. So I guess the thing that I'm saying here is I don't like the fact that I'm getting some positives and some negatives. I really just want straight up distance. I don't just want like distance is a positive quantity, right? So these negatives are also bothering me. So the good news is that there is one very good fix that helps us out with both of these issues. One, I don't really want negative numbers in here because I don't want to have two deviations from the average cancel each other and suggest no deviation. I want them to, in a sense, say, look at all this deviation we have, not like, oh, look, all of our differences canceled. The other thing that I want here is I want to place more emphasis on values that are much further away from the average than others. And so what we're going to do to sort of fix this, is we are going to compute the square of each of these values right here. And so I'm going to write now, I'm going to kind of step away from this table that I'm making, and I'm going to write the more general formula for standard deviation. in general, we will denote standard deviation with a Greek letter sigma. I just drew a pretty mediocre sigma right there. Maybe that's a slightly better sigma right there. In any event, it's this little O, but with like a hooked top on it right there. So sigma, lowercase sigma. Oh, by the way, this is a lowercase sigma. This is our capital sigma right here. So our standard deviation that we're looking at here, we're going to compute this using some of the summation notation we just saw. So our standard deviation computation is going to say, we want to look at how much deviation we see between our average, x bar, and one individual observation, x sub I. What I want to do though is so this x bar minus x sub I, that's exactly these 5 values right there. X bar minus, or I guess I have it the other direction right here. We're going to see in a second. It doesn't matter anyway. Because what I'm going to do is I am going to square all these values. The good thing that squaring does is that any number squared is a positive number. This ensures that we're always accruing positive amounts of distance from the average to help us describe the spread of our data. The other thing that this does, this helps emphasize points that are very far away from the average, helps make our standard deviation grow quite a bit more. If you're very far from the average, then the number that we're squaring is going to be large. And when you square large numbers, they get very large. And so that's going to help add extra emphasis to far away points to say, yeah, our data is very spread out. Even if it's one point that's very far away, that's going to make a large contribution to the overall standard deviation that we're experiencing. So we want to add up all these. So I'm going to put my sum symbol right here. And by the way, typically, in a technical sense, these summation symbols should always get your lower bound on the bottom and the upper bound on top. But it's also shorthand when using these summation notations that if you don't indicate the lower bound and upper bound for the sum, that just is implied that you mean all of it. So in this case right here, I'm just going to write just summation of these squares of the differences. And we're going to divide this whole thing by the sample size. But now what you should notice is that we added up a bunch of squared values. And so what we're going to do to, in a sense, resize this is take the square root at the end out here. So we're going to break this down into a bunch of steps right here. And let's go ahead and do this by hand computation for the standard deviation. So what I know is that this is sort of part of what I want to do right here. All right. I'm gonna accrue all of those and divide overall by n. So I think that my computation is going to look a little something like this. And here's what I'm going to do, by the way. This gigantic square root symbol always kind of drives me nuts. So I'm going to, there we go. There's square root right there. And I'm just going to use it sort of like a function notation. The square root of, well, what do we got here? We've got our average is 3 minus our first value squared plus our average minus our second value squared, plus our average minus our third value squared. We just go on down the list. Notice, by the way, real quick, if you haven't computed your average yet, then you have no way of computing standard deviation. You have to know the average and the sample size to be able to compute the standard deviation. And here we'll do a little division by n. Ooh, and it actually just occurred to me. Let me look real quick at something. Hang on a second. Go away. I just want to make sure that the things that I'm saying right now are exactly matching the book. I'm going to point out to you in a second that it turns out that there are actually a couple alternate forms of standard deviation computation. We're going to talk about those. Unfortunately, those aren't going to come up until a little bit closer to chapter 4 and 5. But there's distinctions between computing a standard deviation of an entire population versus the standard deviation associated with just a sample. In this case here, I am interpreting this as just a sample, and so sorry. All right, that's what I thought I was going to find right there. Okay, one tiny, tiny distinction here, and this comes up in So this is a thing that bothered me for a really long time right here. When we are computing a sample standard deviation, it turns out that dividing by one fewer than the sample size ends up giving us a better representation of the spread of the data. This is something that is very difficult for me to mathematically justify to you. This is something that wasn't made clear to me until I was in grad school taking a 500 level statistics class that was heavily dependent on some calculus knowledge here. So this is sort of one of those dumb little things right here where I I don't quite have a lot to tell you right here about this one other than in general for sample standard deviation, we are always going to divide by n minus 1 rather than the typical n that you would see sitting out front with an average, right? When we compute an average, we divide by how many things we had. When we compute a sample standard deviation, we'll always be dividing by one fewer than the number of the objects that we've had. And again, the 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 justification for that is a little deep. And when I say a little deep, I mean like not a little, like kind of a lot. And so we're not going to quite talk about that one right here. But again, we can perform this computation right here, right? It's a little bit hairy, but we have some notation to describe it. We can write it as one nice statement right here. So let's just do some simplifying here. Square root of, and it looks like I'm going to be getting here 2 squared plus 1 squared plus 0 squared plus 1 squared plus 2 squared. And I guess, okay, I'm going to be appropriate here and include my negatives, but they're all going to go away in a second because we're going to square that stuff. So let's see if we can add this up. So this should be the square root. We're going to get a 4 plus 1 is 5. And then another 1. Oh, thank you very much. Forgot to bring my stuff back up here. Oh, I see what I got. Okay, okay. Okay, there we go. Thank you very much for pointing that out to me right there. Okay, so let me back up one quick second right here. So now that I said a bunch of things about this, all I really was talking about is the fact that I originally wrote this as n down here because I think for average you divide by n objects, how many you have. But it turns out there's some pretty deep mathematical justification that will argue that n minus 1 is a better divisor here when we are computing our standard deviation. So don't worry too much about that technicality right there. And again, when I'm looking for hard standard deviation computations from you, I'm going to expect you to just use technology anyway, and this will all happen for you. All right. So in here, I have all of my 5 terms squared, the differences squared. I did the subtractions. I know that these positives or these negatives right here, I know that I could have probably just ignored those because I'm going to square everything anyway and it's going to end up positive. So it looks like in total we have 4 plus 1 is 5 and then 1 plus 4 is 5 for a total of 10 on top. So 10 over 4. So that's going to say to me the square root of 2.5. And I can go to my handy dandy calculator here and compute some square root of 2.5. And that's going to tell me 1.58 is my 2 decimal round of the standard deviation right here. So I'm going to say here we have by hand computed our standard deviation here as 1.58, right? So here's our general formula. And I know that this looks really hairy. There's a kind of a ton of stuff you haven't seen in here before. I'm assuming that most of us haven't seen this sigma for the summation symbol. This says add up a bunch of objects. What objects are we adding up? The differences, excuse me, the squares of the differences of each data point from the average. X bar is the average. It never changes. It's always 3. The average of this data set is 3. Each individual data point, each x sub I, in a sense, changes. That's our 5 data points right there. 1, 2, 3, 4, 5. We're always going to divide by 1 fewer than the sample size whenever we compute a sample standard deviation. And at the end, we take the square root, and the job of the square root, in a sense, is to undo the squaring that's happened out there to sort of scale these things back down. Now, I do want to say, any of you that have taken algebra out there should know that if you square a quantity and then do some things to it and then square root it, you're not quite getting back to exactly where you were, but we're again, this is still a good representation. So this says to me that a typical data point or a typical data points might fall within some number of standard deviations of the mean. So a lot of the statements that we're going to be making in the future here is going to be based on specific distributions. And we're going to say things like, if our data is normally distributed, if it has a bell-shaped curve, then we'll be able to make statements like 95% of all data points fall within 2 standard deviations of the average. So in that case, it's very helpful for me to know the 2 standard deviation, or what the size of 1 standard deviation is, because then I can measure where are the bounds where I should expect 95% or whatever percentage of our data points to end up falling. So we're definitely going to be using this standard deviation pretty heavily over the course of this semester. We're not going to be doing tons of by-hand computations with this. I am on the homework going to ask you to do this once, because it's meaningful to do it like once. But for the most part, if I ask you to get a standard deviation of a data set, then technology is your best friend here. And I do appreciate that the book 2 different times says, listen, like, don't go spending 20 minutes computing a standard deviation by hand. Nobody's done that in 50 years. Use technology to help you compute lots of these values. But again, in a simple case with a crazy simple data set of 1, 2, 3, 4, 5, yeah, you should be able to do this by hand. It's not going to kill you. And I promise to not make you do it a bunch, as long as you can appropriately choose use your technology when appropriate and be able to do it by hand if I ask here. And then we'll all be good there. So we've computed a standard deviation here. The only other thing I wanted to say here is what the variance is. In this case here, we have that the variance, which we're going to use less, but is an equally good descriptor. The variance here is just the 2.5. The variance is what you get when you don't have that square root on there. Our standard deviation here is the square root of the variance. And so that's going to be square root of 2.5, and that's our 1.58. So hopefully you can see that since variance and standard deviation are just a square or a square root of one another, they're in a sense encapsulating the same information. But what we won't get later is statements like 95% of the data fall within 2 variances of the average. That's just never the way that it's going to be convenient for us to measure where our values are located. So while variance and standard deviation ultimately are encapsulating the same information, they are not, we'll typically use standard deviation, and they only differ from each other by a square or a square root, depending on which direction you're going relating those guys. So you'll see the book refer to variance. And variance, I like the name of variance, it's referring to variation, but again, standard deviation is going to be one of our most important statistics that we will use over the course of the semester. We're not going to compute them all the time. It'll often be given to us, but we will use and interpret standard deviations extensively this semester here. So this quantity matters. This symbol right here matters. We'll be using this quite a bit as well. So let me just kind of write my conclusion for this thing right here, and then we'll look at our next example right here that I've been aggressively moving down the page here this whole time. What we have found here was we found our mean was 3. Our median was 3. Our mode is none. And our standard deviation, 1.58. All right, so let's compare this to what's going to happen here now in a second. All right. So when we go to look at our next data set right here, we're just going to do the same exact thing. And you should see that the only thing that I have done is I have just stuck a 0 at the end of 5 right there. 1, 2, 3, 4, 50 is now our data set. So this should take me about half the time to compute all these things since we've sort of talked through them all. What I would like to do at the end is then say, what impact on our statistics was seen by changing 5 to 50? So let's go ahead and knock these out. To compute the mean, x bar, we're going to add them all up. Divide by n. 1 plus 2 plus 3 plus 4. 1 plus 2 plus 3 plus 4 is 10. Plus 50 is going to give me 60. It's all going to be divided by the 5 data points that we have. And that's going to give me 12 as my x bar value, as my average value here. We're seeing 12. Last time we had 3. Now we have 12. We can go ahead and we can compute our median for this data set, and I'll compute my median the exact same way as I did before. Since all of my data points are already ordered, I can just chop them off from the outsides to see what's left on the inside. Chop off the outermost, chop off the outermost, and oh, what do you know? It looks like we've landed with a median which we denote as capital M, of 3 again. We got 3 again, just like we got before. So the entire reason that we're kind of doing a very similar data set a second time right here is to show you that it looks like changing one value rarely has an impact on the median. Changing one value could have a huge impact on the mean. Our average is now 4 times larger than it used to be, but the median didn't change whatsoever. Right? We're gonna kind of make a better statement about that at the end, but that's kind of the difference that I want to highlight. We'll write a nice sentence about that and give some vocab words to that here in a bit. Let's go ahead and compute our standard deviation here. Our standard deviation, lowercase sigma. It's the sum of the differences between each data point and the average squared divided by n minus 1, and we take the square root of the whole thing. And so when we compute our standard deviation in this case, I've computed my average to be 12. So this one's, by the way, this looks like some numbers are going to get, that last one I could do pretty much the whole thing in my head, but the square root, this one's going to be a little bit tougher right here. So my average that I'm working with is 12 for x bar. So it looks like I'm going to be getting, and I'll do my little same thing here, square root of this whole thing. So I'm going to get 12 minus 1 squared plus 12 minus 2 squared. And you should notice that now what we're accruing here is way more difference from the average, right? Because I think the point to me here is that before, all of our data points were relatively close to the average, and so each individual contribution that each individual data point makes to the overall standard deviation was small because everything was close to the average. Now, you should notice that 12 is a pretty overall horrible descriptor of the center of this data set, or describing the average value of this data. If you tell me that the average is 12 of something, I'm really just not expecting to see 1, 2, 3, 4, 50. I think that 3 is a much better descriptor of the location of the center of this data, even though that 50 is huge right there. Maybe there's something else that we want to say about 50 rather than incorporating it into this average computation right there. So what we're going to see is we're going to get a very large standard deviation, and I'm going to argue that I think that that's going to be, in a sense, a bit deceptive because of the fact that, like, most of our numbers are pretty close together. Most of our numbers don't deviate much from each other. 1, 2, 3, and 4 are all kind of hanging out together. They're buddies there. It's the 50 that's really screwing all of our stuff up right here. So let's go ahead and do this computation. We'll see we're going to get a pretty large value here. The contributions from each of these parts is a large number now. So I'm getting the square root of 11 squared plus 10 squared plus 9 squared plus 8 squared plus 38 squared. I'm doing a little bit of shorthand now. You should notice that technically that should be a negative 38 squared, but anytime I square a number, it's going to become positive. There's never any negative parts that you're going to end up with in your standard deviation computation. There's a subtraction, but even if you get a negative, when you square it, it becomes positive. So I pretty typically just, that 38 to me is just a number that's going to get squared right there. So I very much need help from my calculator here on this one here. So I'm going to go ahead and add up those squares. 11 squared plus 10 squared plus 9 squared plus 8 squared. I'm getting 1,810 over 4. Now when I do my division and do my square root, I'm getting 21.27. Whew. I hope that you agree that this does not feel like an appropriate description of this spread of this data, right? Most of the data points are like 1 unit away from their next most adjacent data point right there. So I don't think this is a very good descriptor of our standard deviation here. We can compute it to be that. We can do this computation, but again, we always want to ask ourselves, is that statistic really doing a good job of describing either the center or the spread of our data? In this case, I think I would make the argument 12 to me is not as good of a measure of center of this data as 3. Right? I think that 3 is doing a good job, a great job, in fact, of describing most of our data. and it's doing a bad job of describing one data point. On the other hand, 12 does a very mediocre job of describing all of our data points out there. So I kind of like the median because the median is a good descriptor of most of our data. The standard deviation we are going to discuss here is always going to end up being, in a sense, partnered with the average. You can see here, if we really aren't interested in using the average to describe our data, then it's good for us to also avoid using the standard deviation. These two are very much partnered together. Mean and standard deviation are a pair. Median and interquartile range are a pair, which we're going to compute here in a second. So some of the concluding statements that I want to make here are these. I'm going to go ahead and type these out instead of writing them here. So some things I want to conclude. So what we saw was that changing a single data point had a huge impact on the average, but had no impact on the mean. Generally, we say that, and I'll do like a little bullet list here. So we refer to our measures of center as being resistant or not. The mean is not a resistant measure. It does a bad job of resisting the effects of what hopefully you have in your head, the sense that that 50 in our data set is a good descriptor of an outlier, right? That one outlier had a huge impact on the statistics that we ended up computing that were based on it, the mean and the standard deviation. On the other hand, we say that the median is a resistant measure. It is not heavily impacted by individual data points. So I want to come back now to what the book does. And again, this is actually kind of relatively different than what I've seen in the past, this whole distinction between measure of center and measure of location. When the book says that the median is a measure of location, you should notice that when we compute the median, it does not matter actually what the values here are at all. This number on the end could have been 50 trillion, and the median would still be 3. Right? The median doesn't care about the actual values themselves. The median cares about where those values are located relative to the other values in the data set when you have ordered them from smallest to largest. The mean doesn't care at all about ordering or location. The mean really cares about sizing. The mean says that 50 was huge, therefore it has a huge impact. The median just says the 50 is the last value, and so it just does the job of being the last value, right? Again, for the mean, if this was 50 trillion, that would have a huge impact. If we're talking median, if this value is 50 trillion, the median would still just be 3. So in general, we refer to the mean as being not a resistant measure. It does a bad job of resisting the impacts of single data points. The median is a resistant measure. It does a very good job of not being overly impacted by one data point. And that matters to us, right? What we, there's so many outliers that exist in the world. What we don't want to do in all, in some cases, there are situations where these outliers are really going to mess up the descriptors that we have of our data set. The median is just not going to be as heavily impacted by those outliers. And so it is sometimes a more trustworthy measure of the center of our data. It is just less impacted by single data points. And we don't want to give too much power to one data point. If we want to treat everything equally, then it's going to be better for us to be using the median here. But we'll also talk about other reasons in which we prefer one of these over the other. So I think that's good for us for scenario 1. Let's go ahead and talk some scenario 2 stuff here. We're going to use Excel to compute a bunch of quantities that are associated with scenario 2 here. 1, because there's a lot more data points. 2, because as you saw, that was slow up there. And I got plenty to say anyway. Let's take a look at some more things of interest right here for computation. So a researcher is interested in studying wait times at an airport, right? So when you go to an airport, you've always got your ticket and it says your flight departs at 2:30, and it's like, as Americans in particular, because our public transit system is stranger than in every other country. It's very rare that things like leave on time. It's a very American problem. So what we're interested in knowing is, on average, how far off from your intended departure time was your flight? So what a person might do is go to the baggage claim area, right? Now that's going to be an area where everybody has just gotten off of a flight. So if I'm in the baggage claim, I know that everybody just was on a flight. And suppose this researcher randomly selects 24 people that have gotten off their flights here and asks them, how many minutes later than scheduled did your flight leave? You should notice here a couple things. One possible response is zero. If I say zero, it was 0 minutes later than scheduled, which means the flight departed exactly on time. You should notice in our data set there's a few negative values over here. That's because their flight actually didn't leave late, it left early. And I kind of laugh because in my experience, every time I've flown from San Francisco to Eureka, I have either been this person, because everybody knows exactly where they go, right? It's just a bunch of Humboldt people getting on a plane when you're flying into McKinleyville there. And it's usually people have been sitting around waiting all day to get on that last flight anyway. Or the fog has rolled in and I'm this person. I feel that the flights from San Francisco to Eureka are usually experienced on the outside of those flight delay times right there. So what we want to do is we want to analyze this data set. What we want to do is compute some statistics of center, mean, median, and mode. We want to compute some statistics of spread, which are officially more like our interquartile range and standard deviation, but we kind of need to compute some of these things along the way. So I've sort of bolded the things that are like truly the important thing, but everything here is something that we should be able to identify. In general, especially before we go graphing any things or try and make any broad interpretations, it's always good that we stop and look for some special data points. So we'll compute outlier boundaries and determine which values are outliers. And finally, we'll look at a couple different graphical displays, the histogram and the box plot, and what we want to interpret from them. Skewness is not a graphical display. Maybe I should do this to be ever so slightly more clear. But skewness is an interpretation that is very difficult to make from raw data and is very easy to make from graphical displays of data. So we want to interpret the skewness of the distribution once we look at the histogram and or box plot here. So let's go for it. What we're going to do with this, though, is I don't want to do like any of this by hand. Even just doing the average by hand here, or even with a calculator, seems like annoying to me. So what we're going to do is we're going to pop into Excel for a bunch of the last of this stuff right here. And Decimal Prince, you are saving me today. I very much appreciate your second catch on me right there. Thank you. Now we have audio. Okay, so now that we're at this scene right here, I've got my Excel and my Word right here. What you can see is I have already kind of typed out my list of times right here. There are a total of 24 times. So my sample size for this data set here is 24. And what I'm going to do is I'm going to show you guys some computations that we can do in Excel here to kind of make this happen for us, because we don't want to have to necessarily do all this stuff by hand here. What's more important is that we are able to use and interpret these statistics computation is not exciting. I want to know why and how, not so much what for lots of the questions that we ask here. So I've got all my times right here. And so let's go ahead and compute a couple values associated with these. I'm going to fill them in over here. Eventually, once we get to some other terms here, I'll go full screen on Excel here so we can see slightly better. So let's compute a few things. I'm going to do a dumb little scroll right there, and I'm going to just give myself some things right here. So typically when I do things like this, and I mean, honestly, I do like exactly this all the time when I'm like computing, when I want to see like how everybody did on a test or something like that. So I'll often give myself things like put in words in a box like average, median, standard deviation. What else are we? Well, I'm going to do a bunch of these by hand here. I think those are the three. And in fact, I don't even know that I care about this one here. I want to get the things that are hard for me to do done in Excel. A bunch of these are going to be easy for us to do just by glancing at the data, so we'll do that. So how can we go ahead and actually compute these values? If you want Excel to perform a computation for you, then you should start by pressing equals. That indicates to Excel that it needs to compute something and produce an output for you, equals. So what do I want this to be equal to? Well, Excel has lots of built-in functions, and one of them is the average. Oh, it doesn't show the drop-down menu? Seriously? Hold on. So there's a drop-down menu right now underneath average, and it's not being shown right now. Let me see if I can add that. That's crazy. Oh, but I won't be able to see it. I don't think I can. See here. It's gonna leave it there for me? Nope. Interesting. That's a little annoying. Okay. Okay. Remove. Okay, here we are. We're back. So here's the important thing. As I'm typing right here, and if you're typing the exact same thing, then there's going to be sort of like a drop-down menu. You can't see it right now, which is really annoying, but on my screen, I promise you, I'm hovering over like a list of selections right here that is invisible to you. But if you're typing this, it's visible. I can't get it to display that on my display screen right now. In any event, you're going to see a bunch of different options right here, but they're all just all the options that start with AV. And you can just either continue to type out average or just click on average right there. It will suggest to you all uppercase. I don't do that because it never matters. What values do we want to average? I'm going to throw this in some parentheses right here. Did that stupid. Oh man. Now I'm doing it to myself. So in my average, within some parentheses right here, I just need to describe the span of data. I see that this starts at the location B2. B2 is my first time of interest, so B2. And notice B2 became blue, and the lettering B2 over here is blue. I want to indicate all the values from B2, it looks like down to B25 seems to be my last row value right there. So I'm going to do colon, that says go all the way through B25. And you can see now, the really nice thing is that it does show exactly that this is the data of interest that has been selected right here. So now when I hit enter, it's going to automatically compute this average for me. And we're seeing we're getting 25.416. So I'm going to go ahead and throw that into my Word doc over here. 25.4167. I'll keep the decimals since I got them right there. Our good rule of thumb this semester, by the way, if you're unsure about decimals, I'm going to say you should always keep at least two. If you've got a calculator giving you more, then you don't have to do any work to keep those. So just keep those. And I would encourage you to do that. So we can do the same thing for the median here. I can do equals, start typing median, and really there's only one option that looks like median. What values? Well, the same ones, B2 through B25. So I do B2 colon B25, close my parenthesis, and hit enter. And it's going to tell me that my median is a nice clean value of 9, which, by the way, we're going to go and do that by hand here in 1 second. For the mode, I think it'll actually even do the mode for us here. I don't know why we'd need, well, this helps for huge data sets, so. Yeah, mode. Yeah, okay. We need the mode for B2 to B25. And it's going to tell us now. Notice an important thing that happened right here. I got 0. Don't accidentally interpret that as no mode. If you scroll up, remember, one of our huge lessons from this whole chapter is you have to look at the data. The most common result that we saw was these 3 zeros right there. There were 2 5s, 2 7s, 2 12s, but there's only one entry that there were 3 of. So because 0 was the most common response, 0 is the mode of this data set. And I'm thinking also, by the way, as a statistician, I might always stop and say to myself, that's well, like, why might I have gotten these 3 right here? And one of the things that I'm thinking is that if you're going to just walk over to the baggage claim, there's a pretty decent chance that a bunch of people that you're going to talk to are on the same flight. So I'm kind of picturing like that's probably 3 people that I just accidentally surveyed that were all on the same flight and they're giving me the same information about the same flight right there. So maybe this is our indicator that maybe this is not the best way. Maybe we should actually be looking up individual flights rather than asking individual people. But that's an issue for our researcher. We're doing the computation here. So let's back up 1 second real quick here and notice, and I'm going to do a thing I'm going to maybe regret here, but that's okay. I do lots of things I'm going to maybe regret. That happens all the time. So why are we, there we go. So if I was really looking for my median here, otherwise, I could have done what I did before. Okay, I'm going to try to not demolish my data set here. And we could have just chopped off data points from end to end. So I'm just putting dots over the ones that I've already accounted for. And I'm just weaving back and forth here. So I've chopped off 3 from each end, 4 from each end, 5 from each end, 6 from each end, 7 from each end, 8 from each end, 9 from each end, 10 from each end, 11 from each end. And now I notice that there are only 2 values remaining right here. I kept on chopping off from the outsides, but now I can't keep going and chopping any further because I had an even number of data points. So it looks like what we're always going to do in this case here is take the average of those 2 remaining values here. And so this is 8 plus 10 over 2 equals 9 is what we're getting for that median right there. It's the value that's sitting exactly in the middle. Half of all of our data points are below the value of 9. Half of all of our data points are above the value of 9. That's our interpretation for that median right there. So let's go ahead and look at our next 2 rows of information we're interested in here. Min-max range, Q1, Q3, IQR. All of these are things that I can get literally, it's not faster for me to do these with technology than without for data sets of this size. I can easily see right here that my minimum value is -8. It's the least of all of my values. I can easily see that my maximum value here is 220. And therefore, to compute the range, it's always going to be the max minus the min, which in this case here is 220 minus -8 for a total span of 228. That says that the total gap in time from the earliest departure difference to the latest departure difference was 228 minutes, right? That's the span of all of our data. Q1 and Q3, or I should say, the IQR will be computed based on Q1 and Q3. And the good news about Q1 and Q3 is those are just like medians of half of the data. Q1 is the first quartile or the first 25% of the data. The median is really the same thing as the second quartile, by the way. This is really just the same thing as Q2 because 2 quartiles is 50%. And that's exactly what the median is doing, is saying 50% of data points are below, 50% of data points are above. So in this case, what I can do is I'm kind of recognizing that this is where I just chop my data set in half, right? That's where the 9 just lived. There's 12 data points above it, 12 data points below it. Therefore, I can go find Q1 as essentially the median of the bottom half. Q3, the third quartile, should be like the median of the upper half. So we can go ahead and play our canceling game again from end to end. Cancel the endpoint, or not canceling, but discarding the endpoints to find what's in the middle here. And I am noticing that I am left between 0 and 2, and the number that I know is halfway in between 0 and 2 is 1, right? So I'm taking the average of those 2 values, and I can play the same game on the other end. Just keep on chopping off values from the outside until we're left with the one in the middle. And again, it looks like we are left with two values rather than just one single value. So once again, I'll average those guys, and it looks like Q3 is going to be 19. This allows us now to compute our interquartile range as Q3 minus Q1, and this is 18 minutes. So this is pretty interesting because the thing that we should notice is that overall there was a 228-minute spread of responses that we got, but 50% of our data, the middle 50% of our data, only encompassed 18 different minutes. Right? So that's a really important reason why we like to look at the IQR rather than the entire range, is because the entire range could have been wildly spread out by an outlier. The IQR, on the other hand, is sort of grabbing like the middle meat of the data. This is really where half of all of our data lives. Half of all of our data only has a spread of 18 minutes separating them at most. And that's a good distinction for us to make from the range right here. I kind of feel like I want to add that as a sentence right here. So what I'm thinking here is that in this case, because we had such extreme large values that were not necessarily related to the bulk of the data right here, looking at the range in this case is not necessarily super useful. It is a good general bounding thing to know, like where your min and max is. Those are always kind of practical here. But looking at the interquartile range, this says discard the lowest 25% and the highest 25% of your data points. What's the span of the middle 50% from the 25th percentile to the 75th percentile? Those only spanned 18 minutes. And so that does give me a pretty good sense that most of our data is kind of packed up there towards the middle, and that our data is not necessarily wildly spread out right there. And I think that IQR is a good measure of spread in comparison to the range right there. So now that we've computed some of these numbers, we can compute what is referred to as a 5-number summary. I almost forgot to add this into my little document here until the last minute. The reason is because our book, for some reason, kind of abandons it a little bit. Our book mentions it, but they really only just do it in example. And so I want to write out what this actually is, and then we'll state it here. This is really useful for us for a value or for drawing our box plots. And so I just want to point out real quick here. Remember, the median is like the second quartile. People don't really refer to it as that. Usually they just use the word median. But you could think of the median, capital M, as just the second quartile. It's where the cutoff point is between the upper 50% and the lower 50%. And so calling the median Q2 is completely appropriate. People don't usually do it, but that tells me you know what you're talking about. The minimum in this case is -8. Our Q1 in this case we found to be 1. Our median in this case we found to be 9. It's off screen, but it's just above the screen right there. Our Q3 was 19, and our max was 220. So some of the things that I'm seeing from our 5-number summary right here is this is just a quick little snapshot of the spread of our data. One of the things that I'm seeing is it looks like a majority of the data is all bunched together on the lower end, but it does look like things are getting much spread out further on the upper end. I can see my IQR, my interquartile range of only 18 minutes of time in between Q1 and Q3. I can see that that doesn't get dragged out especially far below that, but that does get dragged out especially far above that. This is our really the only numerical way that I can get a good sense of the skew of this distribution here. in this distribution, since things are spread more to the right than to the left, we would refer to this as being a right skewed distribution because it seems like the data is much more spread out. The tail of our distribution exists to the right. That's where the everything gets all thin. A bunch of our data here is packed up around the left and the middle. The spread is to the right. So we refer to this as being right skewed here. So here is our 5-number summary. And this can help give us a sense of this is like a snapshot. This is like saying you only get 5 numbers to show me how spread out your data is. This is sort of, in a sense, almost like the 0th percentile, although that's not a thing because you can't have data below it. First quartile, second quartile, third quartile, and sort of like the 4th quartile because all the data is at or below that point right there. So in a sense, this is sort of like the 0%, 25%, 50%, 75%, 100% marks of where our data is located there. And based on the fact that there is a huge spread on the right and not a huge spread on the left, we refer to this data as being right skewed here. We can go to Excel and get our standard deviation. And then we just got to hunt for some outliers and draw some pictures, and we're going to call it a day here. So our standard deviation, I'm going to come back over to Excel here. And for the standard deviation, I can do just what we've been doing. I'm going to do equals, and I'm going to type in STDEV, but you're going to see something unfortunate. And again, you can't quite see, like again, I have stuff that you can't see. I'm hovering over stuff that you can't see right now. And if you're typing it in, you will be able to see it. It's just not being shared on my cast right now because of dumb reasons. But STDEV is the Excel indicator for standard deviation. What you will have seen before is that for things like average, you do like equals average, and that's the only option. When you do equals standard deviation, I currently can view 1, 2, 3, 4, 5, 6, 7, 8 different options, and that's kind of disappointing because it sort of says to me like, which one do I want right here? What I'm going to do is kind of make some statements here. So there's a ton of different ways to compute standard deviation. One of the big things that this comes back to, sorry, scrolling away on your right here, is the whole dividing by n minus 1 versus dividing by n thing right here. And again, this is a technicality that I'm not wildly worried about right here. But technically speaking, we want to compute the standard deviation of a sample. So I am going to select the .s version of standard deviation. And from this, do I need to type that? .s. And now I can again give this the B2 to B25 values. And it's going to go ahead and compute my standard deviation for me. Man, is that thing big right there. 50. Holy cow. Almost exactly 50 also. It's pretty interesting right there. It's a pretty broad standard deviation. What we're going to conclude here in a little bit is that we maybe don't think that this is a great measure of our center here, and or our spread, and we'll talk about why. So this is sort of our notes about this right here. Let me move that stuff here. So we've got a computation from standard deviation. So again, this is just to say, in almost every situation this semester, I would have to imagine that we're going to be using that standard deviation from the sample right there. And we're going to talk a whole bunch in chapter 4 about why we never really see full population information here. So our last thing to do is just talk outliers and our graphs right here. So our book talks about one way that's typical to compute outliers. And so I want to kind of make some statements about these guys right here. If our data is symmetric, not skewed, then we typically identify outliers as data points that are at least 2 standard deviations from the mean. So the general ideas for identifying numerically a outlier here, there's 2 different rules for this, but what I would also like to say is, man, it is not necessarily the case that we ever want to have a hard and fast rule for identifying outliers. This is very much a judgment call type of thing. And so I would discourage you from thinking of outliers as things that as a number as either it is an outlier or it isn't. That's a bad way to kind of go about some of this stuff right here. It really depends on the impacts that it has on the statistics that you compute, the graphs that you produce. The general rule of thumb for these is that if our data is symmetric, which our data is not, right? We just saw that this has to be pretty right skewed. We've got a big spread to the right, a small spread to the left. It does not seem like our data is symmetrically distributed around its center. In this case, if our data is symmetric, which our data is not, then in that case, the typical move is to say 2 standard deviations away is what we would consider to be a normal. Anything more than 2 standard deviations, we would consider to sort of be not normal and therefore an outlier. If our data is not symmetric, like our situation that we have right here, since we are right skewed, then it's more common to use the interquartile range to help us determine what some boundaries might be. So in this, and I made a mistake right here. All of the time that we are talking about quartiles, we never combine quartile discussion with average discussion. The median is a quartile. The median is Q2. So when we talk about this interquartile range distance, it's always away from the median because we want to kind of keep those ideas grouped together rather than mix and match the mean and the median stuff here. So my outlier boundaries should be here. I should have, it should be the median minus 1.5 times the IQR, and it should be the median plus 1.5 times the IQR. And this will give me a sense of where my boundaries are at. So our median was 9 minus 1.5 times our interquartile range wasn't it 18, right? Yeah, we had 9 for the median. We have 18 for the interquartile range. And 9 plus 1.5 times 18. And this is going to tell me what 1.5 times 18 is 27, so that's going to give me negative 18. And this is going to be 9 plus 27 is 36. So what this is saying to me here is that based on where a vast majority of our data lives, this is what we would consider typical data responses between 18 minutes early and 36 minutes late. And therefore, we would classify anything outside of these boundaries as being outliers here. So these are what I would consider to be my outlier boundaries. And therefore, we can then go look at our data set and say, hey, did we have any values like that? I can see that none of my values over here were below negative 18. But if we look over to the upper end over here, I do see some values that are above 36. So in this case right here, I would potentially identify 42, 65, 125, and 220 as potential outliers. And I just said a really important word there. I really try to never say something is an outlier. I try to always say something is a potential outlier, and we should then go look and see what impacts maybe removing it has on our data set. Right? We'll talk a lot more about that again coming up here in chapter 4, but identifying potential outliers, potential points that could be so far off from the rest of the data that they're really making your statistics confusing. Maybe it's better for us to go back and redo our computations without these outliers being in here to get a better sense of the data that we're experiencing. So I've found my outlier boundaries because my data is skewed right. I used a 1.5 times the interquartile range away from the median as my rule. If our data was not skewed at all, then we would have looked at standard deviations from the mean instead. This will end up being the typical thing that we're going to do. This idea right there, that'll come about 100 times this semester, starting in chapter 4. But that's because we're going to look at a lot of symmetric distributions for a majority of this semester. This distribution does not seem to be. Now, I've been making a whole bunch of claims about this not being symmetric, and I have not shown you a picture that shows that lack of symmetry. So for our last thing for the day here, let's go ahead and make a histogram and a box plot. I am going to make the box plot by hand. I am going to have Excel make the histogram for me. So let me pop over to Excel here. I think I still got audio here because I'm not doing this dumb anymore. And let me resize my stuff here so you can actually see what I'm doing. All right, so here we are. We're in Excel. I've got my full screen here. All right. We talked about this one a little bit. I think I showed how to make this histogram before. Let's go ahead and make it again. I need to think about what I want my bins to be here. Now, here's my issue. I know that the range of my data is 228 minutes. That's a pretty big range of my data. I am thinking to myself that I know that there's a lot of, in a sense, like gaps in the data. Like, right? Like if we look at these 2 points, there's a 60-minute gap between two consecutive times right there. So I still want to be able to capture some of these small differences that we're seeing in a majority of our data. There's small differences in most of our data, but then there's some huge gaps all of a sudden that end up out there. So this is a great place where it's not super clear what bins we might want to be using. So here's what I think I'm going to do. I'm going to make 2 graphs here and we'll just compare them and decide which one we think is better. Let's look at bins 5 and bins 10. And again, this is just like Tony things. Nobody calls them this except for me. But I'm going to start at what I know is below my lowest time. So like -10, and then -5, 0, 5, 10, 15, 20. And conveniently, if you initiate a pattern in Excel, you can have it continue that pattern for you. So I'm going to drag this out. And I'm not going to go, well, okay. I'm going to go out to 130. The reason I'm going to do that is because I know that Excel is always going to create a last column for me that's going to be more, and I know that's going to end up capturing 220 right there. So just so I don't have to drag this out forever, I can typically always just stop before my last one data point right there. If we're going to do bins counting by 10, then maybe I'll do a pretty similar thing right here. And again, once you establish a pattern, Excel is pretty good at interpreting that pattern and continuing it. This one, whatever, I'll just go the whole way out there to an upper bound that I know will be far enough out there. So again, these guys down here, I'm going to stop early on the bins 5 because the only one data point that goes further than this is 220. And Excel is always cool with putting in a more column out there, more than the upper bound of the last bin, and that'll grab that one. So let's go ahead and make the histograms associated with these bin ranges here. I'm going to go to data up top. Data analysis. I'm going to grab histogram right there. Click OK. My input range in this case is going to be my times column. Notice in this case, I did choose to grab the word times right there. Therefore, it matters that in my bin range, I also grab the heading for that bin range. So I'm going to grab bins 5. We'll do that one first here. And I'll spread it out for all the bins that we have, and I'll click the button here to say, got it. I do want the labels box to be checked. Can I move this so it's there? Okay. I do want the labels box to be checked because I did include the label of times and bins 5 as the labels for those columns. I'm going to put this guy on a new worksheet, so it's going to open up a new tab of a worksheet down there, not a whole new window, but not in this window. I don't need it ordered, I don't need it cumulative, but I do need them to graph it for me, so I do want them to chart the output. And when I click OK, it's going to take me to a new page. It's going to essentially show me the frequency table here is highlighted, and you can see the histogram that it's produced here in blue. This is a great visual representation of this right skew. What you should see is a majority of our data is all packed up around the median here, but then there's a tail out here where things get really spread out to the side out here. This is the right tail of this distribution. This is a right skewed distribution because the tail is to the right. Now, I pretty much never make one histogram in my life if I ever care to make a good looking histogram. So let's, like, I don't know. Maybe this is a good, I think this is actually a pretty good histogram right here. But let's just go ahead and make the bins 10 one and see what it looks like. I'm going to pop back over. So at the bottom down here, it's a little cut off for you guys. There we go. I was overdoing that a little. There we go. There we go. So you guys can see down here now, this made a new sheet for me. You can see I'm down here on sheet actually 4 right now. It's because I've been playing around with this morning. I'm going to go back to my original sheet 1, and I'm just going to do the same thing. Data, data analysis, histogram. It's already got my input range. I just need to update my bin range to be bins 10 instead of bins 5. And I'm going to again put it on a new worksheet so I don't have to worry about locations for anything. And it's going to make a new one for me right here. I am kind of thinking that this is a slightly less good histogram, and the reason why is because we have no way of like avoiding this tail out here, right? There's just a huge spread in this data. I feel like it's, in a sense, we're losing a lot of the fineness of our data when we only have 3 columns that's covering. And so notice over here, 6, 7, 6. Well, that's, what's that? 6 and 6 is 12 and 7 is 19. That's 19 out of our 24 data points fell into 3 out of 8 columns. I think that I would like to see a little bit more of a fine spread of the meat of our data right here. So I'm kind of thinking this is a little bit too much packing all this stuff up into too few bars over here. So I think I would say in this case, I think that the bins of with 10 are doing a slightly better job because this tail looks the same to me either way, right? Like this tail, the right chunk of this graph doesn't look any different in bins 5 or bins 10, but I think I'm getting a better sense of the distribution of most of my data by looking at the bins of with 10 or 5 right here. So again, all histograms, like you should always make 1 or 2 and pick between them at least, or excuse me, at least 1 or 2, 2 or 3 probably, and choose between them. To me, it is a pretty good representation of this histogram right here. It is doing the job that I can see that this is very much a right skewed distribution right here. We have a very tiny tail, a 1 column tail here, and we have like, 3 hours of tail over off to the right over here. So right skewed distribution based on this diagram right here. Okay, so that's given us our kind of our last image that we were looking for right there. I think we like this one better, so I'm going to leave that one up on the screen for our, smush it all up right there. So I want to just come back now and make a box plot, make some concluding remarks, and we'll go ahead and call it a day. So I'm going to come back to my Word and Excel right here. Still got audio, we're good. So the last thing I wanted to do was grab for myself a box plot. You know what? I think I can just go back to Word right here. Let's just do this guy. So for my box plot here, the thing that I'm graphing for my box plot is that the box plot, this is a graph of the IQR, or excuse me, of the 5-number summary. So let me remember what that was. We had that our min, Q1, median, Q3, max, and we came up with that being, I think it was, let me see if I can remember, -8, 1, 9, 19, right? Because 18 was our IQR, and then 220, I think was what we were looking at here. So you should notice that before, in anticipation of doing this, I built myself an axis here. I actually made this like an image in Desmos. This is just an axis in Desmos right here, and I just kind of cut it out right there. Making our box plot is really, really easy right here. As long as I know those 5 numbers, I've got a box plot for myself. So typically the way that I do this, like most important thing for a box plot is you better label your axis with some important numbers that are relevant to the problem that are evenly spaced. And I'm going to shout at you some more about the even spacing of your box plot values down there. Don't unevenly space your box plot values, or else how are you supposed to ever read any information from it? The purpose of graphing is to get a visual sense of the distance between 2 numbers. And so if you ever label your axes down here with non-evenly spaced numberings, then you have lost all ability to visually measure a distance. And so it matters that you always have consistent spacing on your x-axis. So my minimum started here at -8, which is way over here. And all I'm going to do is I'm just going to put a vertical bar right there for right now. I'm going to connect some pieces in a minute, but all I'm going to do right now is just put 5 vertical bars at these 5 locations. My Q1 was at 1. There's that 1. My Q2, the median, is at 9. Q3, the 75th percentile, is at 19. And the upper bound is out here at 220. This is going to go terribly for me right here. So when we make a box plot, I usually just make those 5 sticks to represent the 5 values in our 5-number summary. The middle 3 we will combine to make one box. And typically then we just connect these with a line. Okay, how straight can I do this? Here we go, here we go. Hey, that worked out okay. So some things that I might also do in this case right here is label these with what they are. All right, this is our min, this is our Q1. You know, we're packed together here. Our median, our Q3, and our max. Sometimes, if it's really hard to read these labels, then or the values that we're actually at, maybe you just even write them on there. This does not excuse you from having to properly label an axis. But you are certainly welcome to, provide a little extra information. Again, on this graph, I can see the right skew here. It clearly looks like our data is much, much, much more spread on the right-hand side than it is on the left-hand side. From this image right here, what I can also see is that this is the middle 50% of my data. 50% of all of the data lives in the box. So the point of the box plot is to sort of emphasize the middle of your data, which is expected to always be the stuff that's most representative of your data set. We know that stuff that's outside the middle could very well be outliers and might be poor descriptors of our data set, might lead us to computing not great statistics that aren't good descriptors of our data set. So looking at the box plot can kind of help us identify sort of the important data values here, the middle ones that we're experiencing. So this would be my box plot that's associated with this data right here. And I do want to say, you might see some other pictures for box plots out there. I have seen box plots where people will only go as far as like that 1.5 times the IQR, and then we'll have like dots at some of these other data points that were out there for like the outlier points, stuff like that. I think ours would end up like looking like that. I never do that because, again, I'm always very weary about labeling something to be an outlier. If I'm like, I don't know, never be 100% certain about anything in this class. The whole point of this class is, yeah, maybe that's an outlier. Maybe this is the best representation for that graph. Maybe this is the best statistic to represent this right here. But this is a lot about making arguments for these things. So you might see some box plots if you're looking to have things generated elsewhere that end sort of early, but then have little dots indicating other points that are part of the data set, but that have been computed to be outliers out there. So this would be like, I'm sure that there's some software out there where if you gave it our 24 data points, it would show you this bottom image instead of my top image right here. I'm cool with either. I like the top one better. I'm cool with either right there. So I just want to kind of say my wrap-up statements here for the day. We looked a lot at mean, median, mode, interquartile range, and standard deviation here. So I kind of want to say as my concluding statements here, a couple things. Let's go here. Go down here. So my concluding statements are mean and standard deviation are always a pair. Measure of center, measure of spread. Median and IQR are always a pair. Those are the exact same pairings. It's a measure of center and it's a measure of spread. We don't mix and match. If we have symmetric data, it is going to be most helpful to us this semester to look at means rather than medians. Basically, the deal is you want the mean to always be the smartest or to be the most practical thing for you to use because it's going to be the easiest thing for us to use. You want the mean to be your friend. But what we've seen, especially in our early examples, is that if your data is not symmetric, then the median is a better descriptor Therefore, we'd use IQR to describe spread. So the point here is that we don't want to use statistics if those aren't good representatives of the data. What we saw is that when our data is heavily skewed, that the average is not necessarily the best representation of the data. Again, if we come back up here, we computed this average here to be 25 minutes. Well, I kind of don't like 25 minutes because 25 minutes is located like right here. Like there was only 5 people that waited longer than 25 minutes, but 19 people waited less than 25 minutes. I don't know that that's a super good representation. The average got heavily dragged out by just a couple values that thought they were more important than others. We might actually think these are less important than others if we think they're outliers, and so therefore average is not necessarily a great representation for this data set. But notice that it's really hard to tell that, right? Like you can't just look at this raw data and be like, average isn't going to be a very good thing here. I don't have a way to see that. So what you need to do to help you identify symmetry versus skewness are these things right here. Let me kind of scroll back up and I'll kind of show you a couple things that we typically do. In general, if you see that your average and your median are the same number or are very close together, that is a great indicator that your data are probably symmetric without you having to draw any graphs. This is the simplest, least work way I can judge symmetry of my distribution. Average and median are equal, tells me, or close to equal, tells me approximately symmetric. However, when we change that 5 to a 50, then we ended up getting 3 and 12. These are clearly very far from each other relative to the size of 3, and that indicates to me this is not a very symmetric distribution of data. Therefore, the median is going to be the better representation. In this one down here, we saw that the mean was 25 and the median was 9. The mean in this case is more than twice as much as the median. This says to me these are pretty far apart. Therefore, this is not a symmetric distribution. And further, because the mean is larger than the median, greater than, that tells me that this is a right skewed distribution. If the mean would have been noticeably less than the median, then we would have had a left skewed distribution. So just comparing mean and median is a very good indicator of symmetry or skewness of your distribution. Other things, we can visually see the skewness in our box plot. We can see the right skew in our box plot. As soon as I see this box plot, I say, wow, this data is heavily skewed to the right. Median is the most important representation of the center of this data. And finally, back over there in Excel, we say, oh man, look at this distribution of this data. If I picture the curve that lives over the top of all of these bars right here, the curve that's over the top of these bars has a long tail that extends out to the right. That is a right skewed distribution. Since it is not symmetric, that's our conclusion. By looking at this histogram, I might say to you, hey, based on this histogram, should we use mean or median to judge the center? And you should say, since this is a right skewed histogram, it would be more appropriate to use median because we only want to use the mean, the average, when we have a symmetric distribution. Okay, that was a sort of long conclusion right there, but I think I said all the things that I was interested in saying right there. So, okay, I think I got it all in. I'm gonna leave this as our final screen right here, remembering how do we pick between these. Just because you can compute these numbers doesn't necessarily mean that you should, right? And this is the kind of thing we talked about, is that not all statistics are equally good representatives of their data set. So when we want to choose what is the best representative of a data set, the most important thing you need to know first is, what is the spread of the data look like? Is it left skewed? Is it right skewed? Is it symmetric? We're going to talk a bunch of other shapes that are going to go along with that in the coming weeks here. But for right now, we just want to think, is it equally distributed to the left and right? Or is there a tail to the left, left skewed, tail to the right, right skewed there? Yeah, I think that's all I got here today. I'm going to try and wrap it up since I know I ran a little bit longer than I intended to here today. Hopefully that means that tomorrow then will be a little bit shorter, since I really just want to hit on kind of some of the specific, little bit tougher computations. So for tomorrow, I'm going to pick a couple of good examples out of the book for us to look at those 5 bullet points that I indicated to you on right here. So next video's topics here, we're going to talk about these 5 things in these bullet points right here. And I'll do that tomorrow at 10:30. So I'll see you guys. Hey, I appreciate this. We got a couple more people with us live here today. That's good. Keep doing that. You're certainly welcome to ask me questions in the chat. Infinitesimal Prince, thank you very much for the 2 helpers on my 2 little mess ups right there. Good to see you guys. Happy week 3. Contact me with any questions. Otherwise, tomorrow, Wednesday, 10:30, I'll do part 2 for this week here, and we'll talk about some of the stickier things associated with our chapter 2 stuff here. Have a good one, everybody.